Once a bearing surface has been defined, we also need to specify its constitutive law. The bearing support exerts a distribution of normal compressive stresses through the bearing surface. This distribution combines with the tensions in the bolts to balance the axial force and the bending applied to the bolt layout. These compressive stresses observe a uniaxial constitutive law that governs the stresses and the deformations. The distribution and the magnitude of the compressions depend on how this constitutive law is defined. For a given bearing surface and number of bolts, the combined tension and bending, or the compression and bending applied, is balanced differently, depending on the uniaxial constitutive laws used for the bolts and for the bearing support. The computation is known linear. The constitutive law for the bolts is elastic perfectly plastic. Therefore, if one or more bolts reach the yield stress, then the computation redistributes the tensions from the bolts that have yielded to those that still have not. If all the bolts have yielded, then the load exceeds its allowed limit, and convergence is not possible. In this case, the bolt layout cannot sustain the forces applied. The bearing support's constitutive law is no tension, and is therefore always non-linear. Only part of the bearing surface reacts, the rest of it does not. The compressed zone can react in the part under compression according to a linear or a non-linear constitutive law. If the compressed part is linear, then we need to state the factor m that, when multiplied by the bearing support's modulus of elasticity, EC, gives the modulus of elasticity for the bolts. If m is large, then the bearing support is less rigid than the bolts. If m is small, less than 1, even significantly so, then the bearing support is more rigid than the bolts. As m increases, the part of the bearing surface affected by the compressive stresses increases in size. Indeed, for the same deformations, the normal compressive stresses exerted by the bearing support become smaller. Conversely, as m decreases, the part of the bearing support affected by the compressive stresses decreases in size, although the stresses exerted become greater. Users can define not only linear laws, but also elastic perfectly plastic, parabola rectangle, or trilinear laws for the bearing support. Sometimes a bolt layout anchored to a plate that is subject to bending may exert a rotational force on it about one of its corners. This behavior can be simulated using a constitutive law that makes the bearing support much stiffer than the bolts, for instance by setting m equal to 0.01 or 0.001 if linear. To see what this means, let's suppose that the bearing surface is shaped like this. And let's start by setting m equal to 1. In a combination where there is only bending moment at the section's elastic limit, we obtain the following distribution. If we now set m equal to 0.01 and repeat the computation with the same forces and the same bearing surface, then we obtain the following. In effect, this simulates the rotation about the lower side of the bearing surface. The affected part of the bearing surface is much smaller, yet the peak stress is almost 10 times greater. 4.375 times the bearing support's limit stress compared to 0.495 times in the previous case. Now let's set m equal to 10, considering the elastic modulus of the bearing support to be 1/10 that of the bolts. The resulting distribution is as shown. The part of the bearing surface under compression is larger. The peak stress is lower, 0.210, and the normal stress level of the tension bars is much greater, because the arm of the internal couple is now smaller.